We are starting chapter 6, almost done with the course. Chapter 6 is the shortest chapter in the course, which is nice. So it should not take too long to get through it. And it starts with a section that's very descriptive. So this video is really going to kind of set the stage and use some terminology, some that you should be very familiar with and some that might be a little bit new. So chapter 6, the entire chapter is called differential equations. A differential equation is simply an equation that involves a derivative because the word differential means derivative, differentiated. So 6.1 starts by introducing these idea of differential equations, and then tomorrow we'll look at something called a slope field. We'll kind of split this lesson up into 2 days. So first, when we talk about something being a solution of a differential equation, what that means is if you take that value and any derivative of that value and plug it into a differential equation, it would make both sides equal. So best way to explain it is to actually show you an example. So here's an example of a differential equation. It's not written the way we're used to. We're used to having the derivative isolated, but your derivative can actually be anywhere within the equation, and it's still considered a differential equation. So this has y prime, which is the derivative, plus 2y equals 0. I want to verify that y equals ce to the negative 2x is a solution to that differential equation. Well, first let's talk about the wording here. The word verify means it's going to work. It is not saying, is it a solution? Verify is implying that it definitely is. General solution means it needs to be generic. Generic solutions, what we're used to seeing is a plus c at the end. What you're going to see over the course of this chapter is that location of that c, we call it the constant of integration, does not have to be at the end. It can be anywhere within the equation and we still consider it generic. And that's what you see here for this general solution. So if I want to verify that it's a solution, I want to plug it into the differential equation along with any derivative needed to show that both sides equal 0. So my derivative, I will need a derivative because right here we have a y prime. The derivative of ce to the negative 2x is negative 2ce to the negative 2x. That's going to take the place of the y prime, so we'll have negative 2ce to the negative 2x plus 2 times y. Y is the original equation, that general solution, so we're going to put in ce to the negative 2x. And in order for it to be a solution, I should be left with a true statement. And I am, because this is negative and this is positive. They are identical other than that. So we get 0 equals 0. So that's how we verify a general solution to a differential equation. We replace all the derivatives and the original functions with what we are given and make sure that both sides are equal. To take that a step further, we can make it a particular solution by finding your C value. And we did this in chapter 4. So in order to find a particular solution, I have to be given an extra piece of information. It's called an initial condition. It's essentially just a point on a graph. So you're going to plug 0 in for x, 3 in for y. So 0 equals CE to the 3 equals CE to the 0. So this was our general solution. So to make it a particular solution, we're going to replace the y with 3 and the x with 0, and we get C equals 3. So my particular solution is y equals 3e to the negative 2x. We did that a little bit at the beginning of chapter 4 when we talked about integrating to get a general solution and then using a point to find the particular solution or the C value. When we talk about the order of a differential equation, the order is determined by the highest level derivative that is within the equation. So just to give you an idea of notation, so for first derivatives, you're either going to see y prime or you're going to see dy dx. Those are your first derivatives. Second derivatives, you're going to put y double prime and y dy squared dx over dx squared. That's my second derivative. Third derivative, we do 3 primes, and then we do the 3's. We don't use the third derivative as much. Beyond that, we stop using prime symbols. So anytime we have a derivative higher than 3, what you're going to see is the derivative number will be in parentheses. So if we want a fourth derivative, we would put a y with a little superscript of the 4 in parentheses, or a fifth derivative would have that as well. So that just because the prime symbols start to be a little complicated. If I want to determine what is a solution to it, you could actually have, I've seen multiple choice questions like this in the AP test, where you're given a variety of solutions. They could be general or particular, and you're asked to determine which ones are solutions. The word determine does not apply that it's definitely going to work. This is a yes or no, you have to prove it. The way we prove it is by, again, replacing your derivatives and your original with the given solution. So this is asking you to do a second derivative. So we would call this a second order differential equation. So my first derivative, the derivative of sine is cosine, and then the derivative of cosine is negative sine. So I'm going to replace that negative sine in for the y double prime minus your original function, and I want to see if that equals 0. Well, it doesn't. We end up getting negative 2 sine x on one side and 0 on the other. So this is a no. Then we're going to do the same thing for the next one. A lot of times these will be like Roman numeral 1, 2, and 3, which ones work, which ones don't kind of thing. The derivative of the first derivative would be negative 4e to the negative x. The second derivative would go back to positive 4e to the negative x. So you're going to plug that in, 4e to the negative x minus the original 4e to the negative x. That does equal 0, so this one is a solution. And then the last one, every time we derive ce to the x, we're just going to get ce to the x, because c is just a coefficient that's going to stay put. E to the x is its own derivative. So when I replace my second derivative with ce to the x minus my original, which was also ce to the x, I definitely get 0. So what we see on this one is this one and this one, B and C, were solutions, and A was not. So you'll have ones like that that will ask you, given a series of possible solutions, which ones are actually end up working. From a visual standpoint, we have something called solution curves. I try to put these in different colors so that you can see. We've talked about this a little bit in chapter 4 as well. When you draw a picture of a bunch of general solutions on one coordinate axis, what you end up getting is like this look of like embedded curves. These are referred to as solution curves of the differential equation. We call it like a family of curves with the solution curves. So for example, if your general solution was c over x, you may or may not remember c over x is a hyperbola. Depending on the c value, you're going to change the branches of that hyperbola. So if my c value is positive, we get branches in the first quadrant and the third quadrant. And if my c value is negative, it flips it to the second quadrant and the fourth quadrant. If I want to know which of those solution curves is actually represented, I would have to give you a point on one of those curves so that I could figure out my c value. So visually, that's what solution curves look like. They look like these embedded curves that are almost parallel. I know they're not linear, but they don't run into each other, and they're kind of one inside another inside another. Last thing to kind of intro, and this is going back to what we did at the beginning, there will be times that you'll be asked to verify and find a particular solution. So kind of like what we did at the very start. This is a first order differential equation because it has a first derivative in it, not a second derivative or anything higher. We are given a general solution. Again, notice that C is in the front again. As long as it's there somewhere, we still call it a general solution. Verify means it's definitely going to work. So we'll start with that process. We only need one derivative. So my derivative is just power out front, power 1 less. That's going to take the place of the y prime. If there's any x in your equation, if there's any numeric values in your equation, they don't change. They just stay put. You're replacing just your y's and your derivative of y's. So y prime is going to be replaced with 3c x squared minus 3 times my original equation, which was cx cubed. And I want to show that that's 0. And that's true because these are going to cancel out. We end up getting opposite terms. So verifying is pretty quick on that one. And then finally, in order to find my particular solution, I have to have a point that gives me my x and my y that can be plugged into the general solution to find your c value. So when I put 2 in for y and when I put negative 3 in for x, I get 2 equals negative 27c. C value does not have to be a whole number. This one's kind of messy. It's 2 over negative 27 or negative 2/27. So my particular solution is negative 2/27 x cubed. So that kind of takes you through a lot of things that we talked about in chapter 4, maybe not in quite the same presentation, but it gives you an idea of what a differential equation is, how we determine if something is a solution to it, and how we can go a step further and find the particular solution.